Welcome to All Academic Channel, where questions matter more than answers. You point your phone at a small square made of black and white blocks. Almost instantly, a restaurant menu appears. The same kind of square can connect you to Wi-Fi, open a payment page, confirm a ticket, or lead you to a website. But what does your phone actually see? How can a pattern that looks completely random carry useful information? How can your phone read it when it is tilted or upside down? And why can some QR codes still work even when they are scratched, dirty, or partly covered? Stay with us until the end, because we will uncover the hidden structure inside every QR code. We will also answer a question that matters more than answer. Can scanning the wrong QR code put your information at risk? The story begins not with smartphones or digital payments, but inside Japanese factories. In the early 1990s, factories needed to track increasing numbers of components. Traditional barcodes were useful, but their data was arranged mainly in one direction, across a sequence of lines. A small development team at Denso, led by engineer Masahiro Hara, was asked to create something faster and more capable. Their solution appeared in 1994. The letters Q and R were chosen to express the idea of a quick response, because speed was one of the main goals. The key idea was simple but powerful. Instead of storing information in only one direction, the new code stored it both horizontally and vertically. This allowed much more data to fit into a compact area. But greater capacity created a new problem. A scanner could find a normal barcode by looking for its long parallel lines. A square filled with tiny blocks was harder to locate, especially beside text, pictures, or machine parts. The scanner needed a visual signal that would say, "This is the code, and this is its direction." That is why most QR codes have 3 large square patterns in 3 corners. These are position detection patterns. Your phone searches for their special arrangement before reading the rest of the code. Because the 3 patterns form a triangle, the software can identify the position and rotation of the code. This is why a QR code can usually be read from different angles. Designing those corner patterns was not random. The development team studied large amounts of printed material, searching for a black and white pattern that rarely appeared by accident. They selected the proportions 1, 1, 3, 1, 1. This unusual sequence helps a scanner distinguish the corner markers from ordinary text and images. The 3 large squares are only the beginning. Smaller guide patterns help the reader measure the grid and correct distortion. A clear empty border around the outside separates the code from its surroundings. Once your phone finds these landmarks, it can estimate the shape of the code, correct the perspective, and divide the image into a precise grid. Each tiny black or white square is called a module. Some modules form guide patterns. Others carry decoding instructions, the message, and extra information used to repair errors. The message is represented as binary data, the digital language of zeros and ones. Standardized encoding and masking rules organize the pattern, and the software reverses those rules to recover the information. What can that information contain? It might be plain text, a website address, contact details, Wi-Fi information, or data used by a ticketing or payment system. However, a QR code usually does not contain an entire website, video, or large image. In most everyday examples, it stores a short address that tells your phone where to go online. The amount it can hold depends on the size of the code, the kind of characters, and the level of error correction. The official system defines 40 standard versions. The smallest has 21 modules along each side. The largest has 177. As more information is added, more modules are needed, and the code becomes larger or more crowded. At maximum capacity, a standard QR code can contain up to 7,089 numeric characters. It holds fewer letters, symbols, or binary bytes, because different types of data require different amounts of space. This creates a trade-off. More information produces a denser pattern, which can become harder to scan if it is printed too small, blurred, badly lit, or shown with weak contrast. A simple link often produces a cleaner and more reliable code than a long block of text. Now we can return to one of the strangest questions. Why does a damaged QR code sometimes still work? The answer is error correction. When a QR code is created, it stores more than the original message. It also adds mathematical backup information using a method called Reed-Solomon error correction. This allows the reader to reconstruct missing or incorrect data, rather like solving a puzzle when some pieces are damaged but enough clues remain. There are 4 standard error correction levels. Higher levels use more space for recovery information and leave less space for the original message. At the highest level, approximately 30% of the code words can be restored under suitable conditions. But this does not mean any random 30% of the visible square can always disappear. The result depends on where the damage occurs, how it is distributed, the image quality, and whether important guide patterns remain readable. Covering a major corner marker may cause failure, while damage in less critical areas may still be corrected. This is also why a small logo can sometimes be placed in the center of a QR code. It uses part of the error correction ability. But a logo that is too large, poor contrast, glare, a missing border, or heavy distortion can make the code fail. Error correction is a safety net, not permission to destroy the design. So how did a factory tool become part of daily life around the world? DenserWave made the specifications publicly available and waived its patent rights for standardized QR codes. The system became an international standard. This allowed different manufacturers and software developers to follow the same rules. So a code created by one system could be understood by another. Smartphone cameras then removed the need for specialized industrial scanners. A camera and image processing software could turn a printed square into a bridge between the physical and digital worlds. But that bridge can lead somewhere unsafe. A QR code is difficult for a human to interpret by sight. You cannot look at its blocks and know which website is hidden inside. Criminals can exploit this by placing a fake sticker over a legitimate payment code, sending an unexpected code in a package or message, or directing people to a false login page. The QR pattern itself is normally encoded data. The danger comes from the destination it opens, the information it requests, or the permissions it asks you to approve. Before opening a scanned link, check the address shown by your phone. Look for misspelled company names, strange website addresses, or a destination that does not match what you expected. Do not scan codes from unknown or suspicious sources. Be especially careful if a code asks for a password, banking information, an immediate payment, an app download, or access to your device. For an important payment or account login, opening the official app or typing the known website yourself may be safer. So the next time you scan one of these little squares, remember what happens in that fraction of a second. Your phone finds the corner patterns, corrects the angle, measures the grid, and reverses the encoding rules. If part is damaged, mathematical error correction may rebuild what is missing. What looks like a random mosaic is actually a carefully organized system designed for speed, capacity, reliability, and universal use. Now you know what is proven, what is uncertain, and what actually helps. Thank you for watching this video until the end. If you enjoyed it, please like the video, subscribe to the channel, and explore our other videos to continue this journey through science and daily life. And if there is a scientific question you have always wondered about, write it in the comments. Your question might become the topic of our next video.